Hi everyone. I'm going to talk today about optimizing NAMD for Intel AVX 512, and this is work that was done in collaboration with Dave Hardy at UIUC. In molecular dynamics, we simulate the motion of atoms over time. Due to the limitations and expense of wet lab experiments, simulation is an essential tool for investigating the details of molecular interactions in pursuit of new therapeutics and options for disease prevention. But simulation methods are not without their own limitations. With current technologies, there are not enough computational resources in the world to satisfy the needs of molecular biophysicists. It is therefore critical that we continue to push boundaries on time to solution in order to expand the capabilities for researchers at many HPC centers. NAMD, developed at UIUC, is an established MD code popular in biomedical research with numerous contributions to the field. MD algorithms are sophisticated, and they cover a variety of parallel algorithms. The direct force component of in-body algorithms is typically dominating in the number of mathematical operations. On the right, we show an example equation for the direct force math. The key things I want to point out here are that this involves a loop over all pairs of atoms in the system. There are a lot of mathematical operations and transcendentals. There is distance-dependent conditional math, and finally, use of constants that depend on atom types of the interacting pairs. Because the direct force component of the interaction falls off rapidly with distance, a cutoff is typically used, so only close atoms are evaluated. A neighborless build is used to achieve order and scaling by tracking neighbors within the cutoff plus some additional buffer distance. An example direct force loop structure is shown here, where for each atom I in the system, we loop over the neighbors, check if they are within the cutoff distance, and calculate the result for each pair. Because we are looping over a neighbor list of pairs, and because of the type-dependent constants, significant non-contiguous memory access is involved in the loop. As far as vectorization, Intel's latest vector instruction set architecture, or ISA, is called Intel Advanced Vector Extensions 512, or AVX 512. AVX 512 can significantly reduce instruction counts versus AVX 2. For example, vector registers are doubled, and this can reduce spilling. The ISA includes functionality enhancements with new instructions such as compress and expand, for example. There is full masking support with fault suppression. And finally, there's support for 512-bit vector widths in addition to 256-bit. Additionally, in my experience, developer productivity can be significantly enhanced. Compilers can be much better at generating vector code when complex or branchy loops are involved. For lower-level implementations using vector intrinsics, the ISA enhancements can allow for simpler implementations in my experience. So if you look at NAMD version 2.13 for AVX 512, optimizations are included that we worked on in the past for using mixed precision, optimizing data layout, and vectorization. Vectorization for the direct force math is performed on the inner loop with compiler-generated vector code using OpenMP SIMD directives, referred to in this talk as the OMP SIMD implementation. In terms of the loop we saw previously, this involves parallelization across threads for the I atoms and vector calculations for the neighbors with gather and scatter operations for non-contiguous memory access in the inner loop. To sum up the result for the I atom, shuffles are used. So if we look at the optimizations included in the OMP SIMD implementation, we can see a significant performance improvement on second-generation Intel Xeon Scalable processors with a 63% performance improvement versus the baseline code. Intel has just recently released the third-generation Intel Xeon Scalable processors that were codenamed Ice Lake. The general improvements for HPC include increased core counts with up to 40 cores per socket, along with IPC gains giving up to 1.53x geomean performance versus the second generation. Up to 8 DDR4 memory channels are available, with up to 1.47x string triad versus the second generation. They include support for Optane 200 series, Intel Deep Learning Boost, PCIe Gen 4, and Speed Select. Digging a little deeper into the compute microarchitecture, we see that we have an improved front end with higher capacity and an improved branch predictor. It is a wider and deeper machine with wider allocation, larger structures, and execution resources. There are enhancements in the TLBs, single thread execution, and prefetching, and there are significantly larger caches. So if we look again at the OMP SIMD implementation, but on third generation Xeon Scalable processors, we see a significant gain of 1.57x without code changes. So can we do better for AVX 512? Certainly we don't see a 16x speed up in direct force with vectorization, but why? Well, some of the reasons for non-ideal vector scaling include predication inefficiency. So we have branches for the cutoff and conditional math that result in masking with vectorization, along with peel and remainder code. Horizontal vector operations are used where shuffles sum up elements within a vector register. We get frequency throttling because doing more math requires more power. And finally, we have non-contiguous memory access from gathers and scatters in the loop. This can be significant because current gather implementations are limited by the cache bandwidth. So we gather 2 vector elements per cycle versus doing 32 single precision FMAs per cycle. This can limit scaling from 256-bit vector widths to 512-bit. We get twice as many FMAs per cycle, but only a marginal improvement in the gather throughput. And as a result, the NAMD OMP SIMD implementation is heavily L1 bound with 512-bit vector widths. There are known approaches to optimize for memory access in MD, and these are implemented, for example, in GROMACS and also the CUDA version for NAMD. These types of optimizations can also improve performance on GPUs, but for a different primary reason. However, these have not been previously implemented for the CPU in NAMD. So I'm going to talk about some of our recent work to optimize for memory access with the NAMD tiles algorithm. At a high level, the concept is similar to cache blocking, but for vector registers. We block atomic pairwise evaluations into tiles to improve reuse of data in registers so that we are not going back to the L1 cache as often. In the tiles algorithm for NAMD, atoms are spatially sorted, and an orthogonal recursive bisection method is used to cluster atoms based on the vector or SIMD width. Rather than evaluating atomic interactions in loops at a pairwise granularity, we evaluate the interactions in tiles between clusters of atoms. This significantly reduces the L1 pressure and increases instruction throughput with elimination of many gather operations. This also eliminates some of the horizontal operations for summing up the results with shuffles. So in this example shown on the right, using 4 vector lanes, we have 2 clusters of atoms with IDs 1 through 4 and IDs 5 through 8. We evaluate 4 pairs and then shift the elements in the vector lanes for one of the clusters to evaluate another 4 pairs without going back to memory. This is repeated until all pairs in the cluster are evaluated. The algorithm is not without downsides. A primary one is that the neighborless build for atoms within the cutoff is now a list of neighboring clusters. So if only one of the atoms in a cluster is within the cutoff distance, you still get them all as neighbors. This results in evaluating many more atom pairs than necessary. And this translates to increased instruction count and also increased predication inefficiency from masking out the unnecessary calculations. The trade-off here depends on the direct force cutoff and the arithmetic intensity of the simulation model. For atomistic biological simulations with larger cutoff, this type of algorithm can give significant performance upside, as we see on the next slide. Here, we see an additional 1.55x improvement from optimizing for memory access with the tiles algorithm on 3rd generation Xeon processors. I think it's interesting to look at some of the differences from the GPU implementation in CUDA for NAMD. These include more extensive use of explicit math versus interpolation. The interpolation is performed on the GPU samplers or texture units when using the GPU. On the CPU side, this further reduces L1 pressure and increases the numerical accuracy. The algorithm is integrated into the NAMD CPU load balancing protocols, as opposed to thread aggregation with offload for GPU scheduling. There's increased use of double precision versus single precision for accumulation. A hybrid tiles and pair algorithm is used to allow some interactions to be calculated in traditional pairwise vector loops, and this helps to reduce the predication inefficiency from clustering. Finally, there are some minor differences for using explicit vector maps with AVX 512. With regard to the programming model, for this algorithm, the concept of a vector is tightly coupled to the implementation. OpenMP SIMD has evolved as a model where the developer writes scalar code that is vectorized by the compiler. This is very unnatural for this type of algorithm, and so the current implementation uses AVX 512 vector intrinsics. The implementation is simpler compared to AVX2 due to ISA enhancements. However, there is an alternative. Data Parallel C++, a component of Intel 1 API, offers an abstraction where workers correspond to vector lanes, along with groupings for SIMD or SIMT execution that allow tighter control over the vector algorithm with a high-level programming model. Additionally, it supports portability across accelerator targets. So for example, AVX 512, GPUs, and FPGAs. I'd like to note here that the Theoretical and Computational Biophysics Group at UIUC has established a 1 API Academic Center of Excellence that will focus on standards-based cross-architecture programming in order to prepare NAMD for the exascale Aurora supercomputer. So in summary, Intel continues to provide significant advances in products for HPC research critical for improving healthcare and quality of life. The ISA enhancements in AVX 512 offer significant improvements in developer productivity and performance on Intel platforms. As with most modern platforms, regardless of the vendor, optimizing memory access can be important to allow software to best exploit the high computational throughput available. Third generation Intel's scalable processors can show big gains for HPC. And finally, 1 API tools are free and represent a significant advance for development across a variety of platforms and accelerators. As touched on briefly in this talk, with specializations for CPUs versus GPUs, 1 API is not really a promise of performance portability, but rather a consistent abstraction and language for vector algorithms, data management, and accelerator offload, along with a consistent API for optimized libraries. In the case of NAMD, a significant fraction of the code could be shared, and so I see high potential for reducing developer efforts for codes that run on many platforms. With that, I'd like to thank everyone for listening. I hope you found the information interesting.